This is the BBC.
This podcast is supported by advertising outside the UK.
Thanks for downloading the In Our Time podcast. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello. In the beginning, runs one secular account, was the Big Bang. All matter in existence today originated around 13,000 million years ago in a phenomenally hot, extraordinarily condensed primordial atom that exploded with incredible force. Hydrogen and helium were shot across the firmament, gravity caused the gases to condense into clouds, and in these clouds the first stars were formed. Then galaxies came, and more galaxies in clusters, onwards and outwards, ever expanding. It's still expanding, runs the orthodox account, and may even be speeding up. It's still creating new galaxies, and it continues to colonize more and more infinite space, despite the fact that it's supposedly infinite itself. The word billions dominates all discussions here. So if our universe is expanding, what's it expanding into? If it's already infinite, how can it be getting any bigger? And is there really only one universe? With me to tackle some of the riddles of the universe is the Astronomer Royal, Professor Sir Martin Rees, Royal Society Research Professor in Astronomy and Physics at Cambridge University, and author of a new book, Our Cosmic Habitat. Also here is the independent theoretical physicist Julian Barber. He recently published a book called The End of Time. And Joanna Levin, Advanced Fellow in Theoretical Physics at the University of Cambridge, who has also just published a book on cosmology called How the Universe Got Its Spots. Martin Rees, as I understand it, one of the main planks of evidence for the support of the Big Bang theory is called redshift. Could you explain what redshift is?
It's the way in which we infer the universe is expanding. If I take a step backwards, we've known since 1920 that our universe consists basically of galaxies, each one being like our Milky Way, each one containing about 100 billion stars. And these galaxies are moving away from each other. What I mean by that is that if you imagine elastic strings joining all those galaxies, the elastic is stretching all the time. Now, how do we know this? The way we know it is that when we look at the light from these galaxies, then the further away the galaxy is, the more the light is shifted towards the red. And that's analogous to the famous Doppler effect we're familiar with in sound. If the police siren is moving away from you, it's got a slightly lower pitch. So it's that evidence which gives us the view that the universe is expanding. And I think this is one of the sort of bedrocks of modern cosmology.
If redshift tells us that the universe is expanding, what is there to tell us that it started with the explosion? I mean, going back, I know you've discussed it many times, many people have, but I wouldn't mind having another crack. What does it tell us about the Big Bang?
If the galaxies are moving away from us, then the naive assumption is that in the past they were closer together, and you can work out how long ago they would have been all on top of each other, as it were. And that time is about 13 billion years. So the natural interpretation is that everything was together at that time ago in the past. Now, of course, galaxies couldn't have existed in their present form back then, but the favoured view is that everything started off, as you said in your introduction, in a very hot, dense gas, and it expanded, and the gas cooled and diluted, and at some later stage, maybe after 1 billion years or so, the galaxy starts to form. So the favoured view, and there's other lines of evidence to support it, is that the universe is an evolving phenomenon. It started off at some finite time in the past, very hot, dense and compact. It's been expanding and cooling, and all the structures that we see around us and of which we are a part are the outcome of forces acting on the universe over this immense span of time.
Okay, right. John 11. The galaxies. If all matter originates from the same ball and the same explosion, why isn't it evenly distributed throughout the universe?
In a sense, it is evenly distributed throughout the universe, in the sense that we are nowhere is identifiably the center. If you have a star that explodes, like a supernova explosion, it's clear where the center of the explosion happened, and all matter accumulates on these shells, and it's not evenly distributed. In the Big Bang, by in enormous contrast. If space itself is created and matter is created in the Big Bang, then matter is, in a sense, roughly evenly distributed everywhere. There is matter in every point in space-time, and every point could equally well be the center. Later on, it starts to clump and form galaxies, and that looks kind of unevenly distributed on small scales when we look in the scale of an individual galaxy or clusters of galaxies. But on the largest scales, those clusters seem to distribute themselves evenly throughout space.
Right. Julian Barber, isn't there another mysterious factor involved in building galaxies? What is dark matter, and what does that do?
Well, there's a lot of evidence. This is also going back 70 years, good to a Swiss astronomer called Zwicky, who first saw the evidence for it in the 1930s. You can tell that there's matter around in the universe because of the gravitational effects that it has. I mean, there can be a completely invisible object, and you can see that it's there because things are whizzing around it. And essentially what Zwicky already observed in the 1930s was that the visible matter is moving around faster than it should if we can see all the matter that's in the universe. So there is well known to be, it's virtually certain that there is more matter in the universe than we can see, and it's got the name dark matter, and one of the really great mysteries is what it's made of and exactly where it is.
What is the mainstream physics understanding of the force that causes the universe to expand?
I would say there's a sort of a rather naive idea that that there was a big oomph at the start which sent it all flying, and since then the rate at which it flies apart is controlled by gravity. If there was enough oomph, it'll sort of go on forever and never come to rest. If there wasn't enough oomph, it'll fall back on itself, and we'll go from the Big Bang to the Big Crunch. I have to say I'm beginning to get sceptical about that view, but that's the standard picture. You have to bear in mind that science comes in two parts, at least it does at the moment. You have the laws of nature, or the laws of dynamics, and then you have initial conditions. So when you say what drives the universe apart, in the standard orthodox picture, it's the oomph you give it at the start.
So that's the kinetic energy. And
that's the kinetic energy.
The matter that is formed causes a gravitational pull, and that matter includes dark matter, which adds to the gravitation of the matter we can see and keeps the thing together.
Yes, and there is this very fascinating thing that, according to the standard picture, we seem to be just about exactly on the dividing line between going on forever and falling back. I mean, sort of on the dividing line. And that's very mysterious.
There's a very nice layer of scepticism in your remarks. Use the word naive and mysteriously close. So if I can get that in a minute or two, but go back to Martin. You write in your book, Martin, quote, "We, the stars and the visible galaxies, are just traces of sediment, almost a seeming afterthought in the cosmos. Something quite different and still unknown controls its large-scale structure and eventual fate." Now, those are tantalizing phrases, large-scale structure and eventual fate. What are you referring to? Is this the dark energy now, from dark matter? It's like Darth Vader. We're on sort of Miltonic, Manichaean, Harry Potter terms here, aren't we?
Well, it is embarrassing that only...
Darth Vader, sorry, I got him wrong again.
Only 4 or 5% of all the stuff in the universe is in the ordinary atoms of which we, the stars and the galaxies, are composed. All the rest is in some mysterious form.
Why do you use the word mysterious?
Well, because, as Julian said, the dark matter is something whose nature we don't fully understand. We suspect it's some sort of particles made in the Big Bang along with the atoms and the radiation, but we don't really know what it is. But we do know that there is more dark stuff in the universe than there is in luminous stars and galaxies, and that is one of the problems. But there's an even more mysterious issue that's come to the fore in the last few years, which is that this dark stuff is in two different kinds. There's the so-called dark matter, which holds the galaxies together, and this goes back to Fritz Zwicky in the 1930s. But we've also discovered that even empty space itself has energy latent in it, and 70% of the mass and energy in the universe, as it were, is in empty space itself, not even in dark matter, still less in actual atoms. And this dark energy is governing the way the universe is expanding.
Julian, you want to get in on this?
I just wanted to come in on one point there. there's very few observations which you can interpret without using some sort of theory. And the remark that Martin just made about this extra form of dark matter which causes the acceleration, that conclusion is drawn from using Einstein's theory as it exists now. And that is possibly dangerous. There is some unification, some deeper understanding is going to come. And I think it's almost certainly going to change the theory that we use to describe the universe. And therefore one must take these claims with a certain pinch of salt because they're crucially dependent upon the theory that you use to interpret the observations.
John Levin, can I ask you, at one point in your book, you are very emphatic. You write, the universe cannot be infinite. Well,
it's probably too emphatic for my own good.
Right.
Yeah, and that's true. I did write that. It's not that I think that there's empirical or logical evidence that suggests that it's impossible for the universe to be infinite. It's just that I think it's an untenable idea. If you think about an infinite universe, it becomes extremely peculiar. If there's an infinite universe, it means that there are infinite possibilities. It means that somewhere else there's a galaxy just like this galaxy. It means that there's an infinite number of these galaxies. And there's an infinite number of planets that look infinitely close to the Earth, and somewhere there's people sitting around a table having a discussion about infinity. And it just becomes this kind of absurdist notion, and that might not be pressing enough, but it does start to hint that something's wrong. And
you think something's wrong because we can't understand it?
No, not just because we can't understand it, because infinities seem to be very dangerous things. We usually mark infinities as the failure of a theory.
But then we're measuring our understanding against our own minds. Maybe we're not able to understand.
Well, it actually kind of works. I think of it more as the theory. It's possible that we might just come to a place where we can't understand something, in which case scientists will give up. I think that the scientific impulse is to believe that that's never going to happen. And it's brash, but it does give us progress. And so one of the things we can do, for instance, is look at where Einstein's theory does begin to break down. It begins to break down at things like the Big Bang, where Martin was discussing the very, very first moment is not something we can talk about precisely because the theory starts to give answers that we no longer trust. They're not as predictive. There's infinite singularities. There's infinite curves, infinite energies. And this is an infinity that's not as bad, but is on a similar footing.
I'm myself, too, very attached to the idea that the universe is finite, but that might just be a reflection that my mind is finite. There is something extremely appealing about a finite, self-contained universe because, in a wonderful expression of Einstein, then you have a chance of closing the circle of cause and effect. You can, so to speak, find a total explanation of everything within that. This is hugely attractive. And my life's work really has been devoted to trying to understand the universe in such terms. But every now and then I look at myself with disgust and say, it's just because you're a finite little worm and you can't comprehend the infinite. So there may be a danger in that. But I very much feel in sympathy with what you said, Joanna.
Yeah. If I could just respond to that very quickly. I mean, infinity is a brilliant notion mathematically. So don't reject the notion mathematically, for instance. And it was rejected for a long time. I just think physically we never see infinity in nature, and that the universe was born, as are all of its progeny, and that we are all finite, and everything within this cosmos is finite. And I don't believe that a unified theory, which will see gravity, space, energy, and matter all as different reflections of the same thing, will create space infinite, but everything else finite.
Yeah, just first of all, in praise of the infinite, there's that wonderful saying of David Hilbert, we hopes the mathematicians will be never driven from the paradise of the infinite.
Yeah, that's right. That's beautiful.
I think it might be interesting to put this in a historical perspective. There have really been only about 3 great cosmological models in the whole of human thought. The first really clear one is Aristotle's, which is the self-contained spherical universe, and that was sort of the shell of the stars we see.
And the
then it was and
there was an outermost sphere.
The outermost sphere, the Uranus, the outermost sphere. And beyond that, there was literally nothing. No space, no anything. I mean, there might just be gods out there, but nothing else beyond that. Then you get the changeover in the 17th century to the infinite space of Euclidean space and atoms moving in it. And that was then the dominant paradigm until Einstein comes along. And amazingly, it goes back almost exactly to Aristotle with his closed universe model, which started modern relativistic cosmology in 1917. And that's very interesting. But there, in the meanwhile, the mathematics had come along because there was always a mathematical problem with the Aristotelian cosmos. There's this idea of the people saying, yeah, but if you got up onto the Uranus and threw a javelin through it, it would go on into something. But then in the meanwhile, mathematics had advanced so fantastically, and the idea of non-Euclidean geometry, and one could see that in a way the surface of the Earth or the surface of a balloon is a very good model of space, of how you can have a self-contained space, so that Einstein's model was then mathematically on a far more secure footing. So that's very exciting. But the fascination of the closed universe persists.
Martin.
I share the prejudice in favour of a finite universe, but because we've got to bear in mind it could be finite but much larger than what we actually observe.
Absolutely.
The universe that astronomers can study, although it contains these billions of galaxies, is still, of course, finite. And there could be a lot more beyond what we can so far observe, even in a universe that's not infinite but actually finite. And as far as Jana's concept of the replicas of ourselves, you can work out the combinatorial possibilities and show that even in an infinite universe, you would have to go to a distance far, far bigger than our telescope can reach before you got a duplicate of ourselves, because of all the possibilities, which are a vastly bigger number even than the number of stars in the visible universe. So there's no empirical argument against an infinite universe, and many of the ideas currently popular do suggest a finite universe, but nonetheless much larger than the horizon of our observations.
Well, you're talking about a finite universe in which the redshift still shows we're expanding. So it's a finite universe which is still expanding.
Absolutely.
So that theoretically is possible if it keeps expanding forever. We could sensibly call it an infinite universe.
Well, if it goes on forever, but of course it may expand for much, much longer in the future than it has up till now, but not an infinite time. At the moment, the simplest theories do suggest that the long-range forecast is an ever-emptier universe that goes on forever. But even in cosmology, long-range forecasts aren't entirely reliable.
It just reminded me of a Woody Allen quote where he won't do his homework because he says the universe is expanding, and his mother says, "You live in Brooklyn. Brooklyn is not expanding. Do your homework." And that's pretty much the reality of it. Brooklyn's not expanding, and the Earth is not expanding. As Martin said, the solar system is not expanding. We have sort of, the local forces are more important than this global expansion.
I'd like to give another Woody Allen quote from my book, which is that eternity is very long, especially towards the end.
So but you think it's a finite, but do you think it's still expanding, Julian?
Now, I would really like to come in and really question this dogma that the universe is expanding.
Good.
Because let me start with an interesting historical...
Why do you call it dogma? You just think it's an accepted... Well, you think it's dogma, yeah.
Well,
that's why I call it dogma. What a stupid question.
I should think those professional scientists who are listening to me are thinking I'm committing scientific suicide by questioning that the universe is expanding now when I say it. But I think there are very good reasons to be very sceptical, and even if I'm wrong and the universe truly is expanding and nature proves me completely wrong, I think we need to get to the bottom of this because it will be an important insight. Let me start with a historical observation that when they first saw the redshifts in the 20s, in fact in the teens of the last century, they came up with a completely different explanation for the redshift. The expansion, the stretching of space idea only came in the early 30s. In Einstein's general theory of relativity, there are two so-called redshifts. One is due to stretching of space, but the other is a purely gravitational effect. It's well known that clocks on the surface of the Earth run slower than clocks in satellites going around in the global satellite positioning system. And in fact, aircraft now can only land safely because they take into account these effects of Einstein's theory in working out exactly what's going on and where aeroplanes are. And that's called a gravitational redshift. So there are two possible explanations. And in fact, for a decade, people thought that it was the gravitational redshift, not a stretching redshift, that was explaining the expansion. So that's, first of all, there is potentially an alternative explanation for the redshift within Einstein's theory, and it was the one that was first invoked. Now, secondly, the idea that the universe as a whole is expanding is a very odd idea, and frankly, I think it stinks. For the following reason, if I hold this plastic mug up that I've got in my hand here, I can move it around in this room, I can twist it, I can move it, and I can imagine it getting larger and smaller, and that is all totally meaningful for me in this room because I can compare it with you and the walls. But if that plastic mug was the whole universe, and there was nothing outside it with which to compare it, all of those three operations I've described of moving, rotating, and getting it larger or smaller is completely meaningless. If, as Jana argues, the universe is self-contained, or it's internally denominated, to use a grand philosophical expression, what does it mean to say that it expands? So I think this is very suspicious, and one should be looking for theories in which the universe is not expanding, but it's just changing its shape.
I'd like to come in and give my take on Julian. I think it's very important to think what we do mean by expansion, but I think there are 2 points that Julian's missing out. One is that we have lots of independent evidence that nothing in the universe is infinitely old. The oldest stars we can age fairly reliably. We know they have enough fuel to last a certain length of time. And if we had a universe that had just been sitting there for the infinite past, we'd have to have some implausible story whereby all the stars turned on at some time 10 or 12 billion years ago in synchrony. So I think if there's not an original event, we still have to have an origin in time, which is hard to understand. And also, I think conceptually, Julian is finding it hard to understand the expansion because he has left out 90% of other physics. If you put nothing in physics apart from a continuum of space, then it's true there's no scale. But we know that the universe contains atoms. And when I say the universe is big and getting bigger, I mean it's getting bigger compared to atoms, and it's big in that it contains a number of atoms that's measured by a 1 followed by about 80 zeros. So that's what I mean when I say the universe is big, and that gives a scale to it. So I think we know that there is some other measure of scale in the universe set by atoms and by the quantum. So you can't divide space infinitely. You can't divide time infinitely, probably. There is a sort of underlying graininess. And when we say the universe is big and expanding, we mean that its scale is getting larger compared to that underlying scale. I mean, I think that Julian is missing that out. And just as Einstein was premature in his attempt to get a unified theory because he wasn't putting enough physics, I suspect that Julian is going to run up against the same problem.
I think it's over to you, because I'm going to help you here.
Hold
on just a second. You, can you reply? Because it's a very... Martin made 2 strong points, so...
Let me start with the second one, because that'll be fresher in the listener's memory. On the question of the scale that the atom set, there's no question whatever that is true, Martin. I'm not for 1 minute questioning that. What I'm questioning, but that's at what I would call an empirical level of science, not at the deepest level. We just have to accept that's there. If there is truly a quantum theory of the entire universe, I think it is extremely likely it will explain where those atomic scales come from, and it will do it out of a theory in which there is no scale. And therefore, it may well be premature to talk like this, and after all, Einstein was searching for his unified field theory 70 years before it was, and maybe I shall have to wait for my triumph when I'm pushing up the daisies. So that's the answer to your first one. The second one about the evidence that the universe was very different in the past and that stars formed and galaxies formed and so forth. This I really would say does belong to bedrock, and I wouldn't want to question that at all. But let me just point out that in the current picture, 2 things are happening in the universe. The first is that it's allegedly expanding, but secondly, it's doing what I call changing its shape. And it's changing the shape from being apparently extremely uniform to being much more clumpy. It's still uniform on the large scale, but there's much more clumpy detail. Now, what I'm saying is that the only thing that is actually happening is that the shape is changing and it's not expanding as well. And therefore, I have a past perfectly well. My past is when the universe is completely uniform, or as uniform as it can get. And then we don't measure things by time, because I don't believe that exists, but we measure it by what we can see out there, the structures we see out there. I don't think there's any question that the universe looked totally different in what we call the past. That's fine. So I'm just measuring it by that level of graininess that is in the universe. That's my measure of time. So that, I believe, are my answers to your 2 very good points, Martin.
Well, I was also going to say that the microwave background, which is this cosmic radiation left over from the Big Bang, is also one of those persuasive arguments for a Big Bang that happened everywhere and a universe that is expanding and cooling. It's very, very hard to explain the microwave background in a model that does not have those properties, doesn't have a hot beginning and in a subsequent expansion to today. So this radiation, just for people who are listening, does surround us in every direction. It has roughly the same temperature wherever we look, as far as we can ascertain. It fills the entire space uniformly. And it's a very important relic from the origin of the universe.
That's absolutely true. And at the moment, I have to be absolutely honest, I can do no more than wave my hands in answer to that point.
Martin Rees, I want to come to you to tell us in this final lap of the programme about the anthropic principle, what it is and why it's astonishing, and what you make of it, really.
The reasoning or the thoughts behind this are that when we look at our universe, it does seem as though it is, in a sense, rather specially tuned for life, as it were, biophilic. Julian already mentioned the way the expansion speed seems to be neither too fast nor too slow, so there wasn't a big crunch soon after the beginning, and it's not expanding so fast that gravity loses its purchase and can't form galaxies. So that's one apparent bit of tuning, and as one looks into it, there are other respects in which the laws seem to be rather special in order, in the sense that were they different, we can imagine a universe that would be rather sterile and stillborn, where there could be no stars, no atoms, no complex chemistry, etc. And the question is how we react to that. I think
we're talking about a number of minor differences all along the way. Not minor differences, a number of precise calculations, as it were, all along the way that make it precisely possible for you to be sitting here breathing and talking today, aren't we?
That's right.
And they're all on the edge. They're all, if you take two little bits of that out, or one little, not even a degree, fraction of a fraction of a fraction of that out, there'll be no you, no talking, no today kind of thing.
Yes, we've got to be open-minded about all other possible kinds of life and complexity, but certainly you can imagine tuning the knobs differently so that you could end up with a universe that would certainly allow no complexity. So there is this special feature of our universe. Now, what does it mean? What it means, I think, will depend on the answers to the profound question that Julian is raising. What's the nature of the bedrock laws of nature? Some people suspect that there will be laws of nature which describe in a unique way all the important features of atoms and gravity and the other forces. If that's the case, if the laws are all unique, then we just have to say it's a brute fact that the universe is the way it is. It's a brute fact or it's cosmic design. But the alternative possibility is that when we have this underlying theory, which Julian addressed, it may tell us that the cosmos is a still grander scheme than what we traditionally call the universe, and that there are bedrock laws of nature, but what we call the laws of nature in our universe are just, as it were, local bylaws, and that there are many other universes, the outcome of separate Big Bangs, or maybe separated from us in some extra dimension, which are governed by different laws. And if it were to turn out that way, if the laws of nature were to allow this variety, then that would give an answer to this tuning mystery, because then there could be many Big Bangs, and their aftermaths could lead to universes very different. And if there's a huge number, let's not debate whether it's an infinite number or a finite number, but there would be some in which conditions were propitious for complexity, including us, to emerge.
Thank you very much, Martin Rees, Julian Barber and Joanna Levin, and thanks for listening.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.